Hello, this video will go through some of the topics and problems in chapter 1.5 in PreCalculus. The textbook that I'm referencing is PreCalculus with Limits, and the main authors are Larson and Battaglia. So I'm making this video mostly because I have an honors pre-calculus class, and I want them to be able to get some information if they want through video. So let's go through. And I think I have covered up some of my markings. There we go. Let's see if I can move that out of the way. Okay. So what we are going to look at first is vertical line tests. We're in kind of the beginning parts of pre-calculus where we talk about functions a lot. The vertical line test is something you should have seen in Algebra 1 and Algebra 2, and it helps us determine whether a graph is a function. The rule is that if you take a vertical line and you kind of move it across from left to right, and if that vertical line hits the graph in two spots, then it is not a function. So if we look at, we have three graphs here. The first one you can kind of see they have just one example of a dotted line, and you can see that here and at the point right below it, when that line is completely vertical, straight up and down, it goes through 2 points on that graph. So this one here cannot be a function, okay? For the second one, part B, I guess you would call it, we have another vertical line that's drawn through, and you can see that it just hits that graph in one spot. And when I talk about the graph, I'm talking about the curve, not the X and Y axis, just to clarify. So for graph B, no matter where we drew that vertical line, if we drew in here, if we drew in here, if we drew in here, anywhere we draw a vertical line, we're only intersecting that graph in one spot. So that is definitely a function. And then if we look at the third graph, part C, again, we have, as far as the vertical line test goes, this could probably be called a piecewise function. But regardless, this vertical line test also only goes through the graph at one point at a time. So it does pass the vertical line test. And you can see more information in your textbook. Every video that I make for this class, I should say that I'm expecting you to go through the chapter itself. This is not going to be comprehensive. This is going to kind of touch on the basics and or how to do some of the problems. So let's see, what else are we going to go through in chapter 1.5? It's called graphs of functions. We just talked about the vertical line test. We're going to talk about finding domain and range from the graph, zeros of a function, increasing, decreasing, and constant. These will be intervals that we're going to identify. And then the extreme, a relative minimum and relative maximum, as well as absolute minimum and absolute maximum. And then finally, we'll talk about even and odd functions. So those are the kinds of things that we're going to go through. And again, I encourage you to look at the textbook as well. So let's see what we have here. Finding the domain and range from a graph. So the domain values are, you can think of it really like basically we're looking at the X's, and for the range, we're looking at the Y's. I kind of sort of remember learning this myself, and I feel like I felt I was overwhelmed. Like, oh my gosh, how am I going to define the domain and range? It just sounded intimidating. And then I think I kind of realized that for a lot of random functions, just start with the fact that it could be all real numbers. They could be defined along all real numbers. If you have a line, any linear equation, generally, you're going to say all real numbers for the domain and the range, unless you have a constant. For this function here, what we're going to do is to find the domain, what we want to do is just look at the x-axis. Okay, I'm going to trace over that. Let's see if this orange will show up. So this x-axis here, and what I'm looking at is where does the graph, what I'm doing is where does the graph not touch? And I don't mean touch the axis, but if I go up from -3, I can see the graph is above that. -1, it is above that. Could have been below it, but whatever. So I can see that the graph is defined for all of these x values. The graph started at x equals -4. So that means that for any value less than -4, this graph is not defined. So what I'm going to put down is that the domain And the domain for this function is for x greater than -4. And I could put all real numbers such that x is greater than -4. So let me just add that in. And there's a symbol for, I'm going to leave actually a space right there where I can go back in. I'm going to make my tool a little bit smaller. So we're going to talk about all reals. And the symbol for real numbers is this. Usually you have like 2 of those like stems on the R. So all real numbers, that's not the greatest. Let me retry that. I'm not going to spend a whole lot of time on it, but you should be familiar with that if you've gone through Algebra 2. So all real numbers for x greater than -4. And actually what I should have said was x greater than or equal to -4, because it does look like it's defined at -4. There's a closed dot there, and that blue dot, that's why I just erased it. So x can be equal to -4 and greater than -4. For the range, we're going to do something kind of similar. We're going to just look at the y-axis. And so for here, what I want to do is, all right, I can see the graph is defined for most of this. Again, I can kind of just like, even though there's, let me just grab my pencil again. Even though on this part of the graph that's being shown, I don't know, like I can't see that for y equals 6 is going to be defined. But if I had moved this, this is eventually, if it had gone on and on forever, I'm thinking big picture, I can see that for all of these values, these y values are all defined. Suddenly when I get down to here, I can see that the graph is not there any longer. So for the y's, for the range, what I'm going to talk about is that it can be 0, right? Because this is the point. Sorry, I'm using the wrong part of my mouse. This here is the point on the y-axis where it's the last place where we see it, and that's where y is 0. So what I would say for the range, I'm going to put all reals. Whoops, not range. So all reals, and then what we want to specify y is, I can't do it in this keyboard, greater than or equal to 0. So I have to go back and put that little smudge for a little equal sign. And again, how do I know that it's equal to 0? Because they filled in that blue dot right at -4. And again, I need to put this symbol here for all real numbers. And so that's how you would determine the domain and range from a graph. All right, let's see if there's another example. For this here, this is just a picture that I grabbed off the internet. I'm not sure why the dotted line is there. It might not have any bearing on what we're going to do. So don't feel like, oh, what does that mean? For this particular problem, it probably doesn't mean anything. So again, I'm going to look at the domain. So that's my x values. And you might think I'm doing the vertical line test. I'm not. This just helps me be really concrete about what I'm looking at. And I can tell that for all of these x values, there is a graph either evident or, like in this case here of this line I'm drawing, it will eventually hit, like it might be way off this graph here, that the piece that's pictured, but if I go out to x or y, way up here off my screen, that arrow here at the top tells me, whoops, I can't circle when I have the line tool, but that arrow up there tells me that it goes on to infinity, and it's going to slightly go outward at an angle. So I do know that for this particular thing, I can see no place where this graph will not be defined for the x values. Okay, so for the domain, I don't have any restrictions. It's all real numbers. Okay, let me erase all of that. For the range, we're going to do the same thing. We're just going to look and see, is there any point here where the range is not going to be defined. Actually, I'll grab my line tool. So again, if I start way up here, I can see that this will go out to infinity. So even if I was to continue my y-axis up, I'm still going to be hitting that graph because this would continue on. Again, I'm not worried that it's hitting the graph in 3 points here because this is a horizontal line. So my vertical line, which doesn't really have much to do with this problem, but in case you were wondering, Again, I can see that this graph is defined because it's hitting when I'm drawing this. I can see that part of the graph. And if I go way down here, like off the chart, again, this arrow says it's going to go down into infinity. So again, for the range, I can see that it's going to be all real numbers. So the graph was a little bit more complicated than the first graph that we saw, but it was almost easier. There was all places it was defined at. So that makes it a little bit easier. This one here we'll talk about again a little bit more briefly. So for the domain, that's our x values. We would say that actually, why don't you pause the video and see if you can tell me. Pause the video, see if you can come up with an answer, and then come back and we'll talk about it. So for the domain, all of the x values are defined, so it will be all real numbers. I can't make the symbol very well here. For the range, for the y values, then it would be all real numbers, but for y greater than or equal to 2. And that's because that's the bottom part of the y-axis. We can see that no, the graph does not go below y equal 2. So let me just make that little mark there and make that little mark there. So all reals where y is greater than or equal to 2. Okay, let's move on. The next part of this is zeros of a function. Kind of the more formal is let f of x be 0 and solve for the independent variables. We'll do a couple of those in just a minute. The zeros of a function are also known as solutions, roots, and x-intercepts. So when we are finding them, if we're giving you the graph, you just look along the x-axis and see where the graph touches the x-axis or crosses the x-axis, and those would be very simple to see usually. We're going to do some algebraically. So let's see if I have any on the back. I do. Find the zeros. We'll do the first problem. If you feel confident at any point, what you could do is hit pause, write down a problem, hit pause, and come back and see what the answer is. So how do we find the 0? This is technically our y, right? I could write it like this. I could drop that function notation. And zeros actually means where are the y, what are the x values when y is 0? So we take out y and put in 0, and then we just solve it. So I'm just going to bring the 2x over, and x is going to be 15 over 2, or 7.5. So that's short and sweet. This was a linear version. There's only one root. The problem number 2 is a little bit more complex. This is a rational function because it's a fraction or a ratio. When we have, if you go back to thinking about fractions in general, fractions are equal to 0 if there's a 0 in the top. It doesn't matter what you have on the bottom. If there's a 0 in the top or the numerator, then it's going to be a 0. So we can just ignore x squared plus 8. I mean, sure, if we were worried about where it's undefined, we would pay attention to it. But for the 0, we just take the numerator, write it over, and say, hey, where does this equal 0? And so we can see that for x equals 5, this fraction will be 0. So that's the answer. Okay, so remember that whenever you have a rational function that you're checking, make a note that that's how you do it. We have one more example down here. Same thing. We're going to take out the function notation, put in a 0, square root of 3x minus 2. So I'm going to bring that over. I'm going to square both sides. So 2 squared is 4. The square root of 3x squared is just 3x. So x will be 4 over 3, or 1.33. So there will be one solution, 1, 0 for that one. Okay, so that shouldn't feel super new. It should be something that you've done before in Algebra 1 and Algebra 2. Okay, let's see what else we have here. This is a great graphic. I like this. Increasing, decreasing, and constant intervals of a function. This is just some new vocabulary words, although you should have seen it technically in Algebra 2. Decreasing, constant, and increasing. You want to read this. So at the bottom it says, when looking at a graph, read it from, and this is really important, left to right. You can't just It's just like we read. So that's nothing new. But I can picture people saying like, well, if I start from right to left, here I would be decreasing. But we always start from the left and go to the right. And I kind of pictured if I had a ball or maybe there was a little bug, like what's happening to this bug? Maybe he's on a little skateboard. So here he is, he's going down, he's flying down that hill, right? So if you're going down a hill, or I guess I had a colleague who said skiing, you're skiing down a hill, it's decreasing. You're going down, decreasing. Here, there's no momentum really. You're just going at a constant pace. The graph is nice and flat. And then what are you doing here? You're going to have to be walking up. So the function is going to be increasing there. So it's just a really good graphic. I feel like in some ways it's kind of common sense, but just the main thing is remember to read it from left to right. All right. So then what we have is some, this can all kind of be lumped together in extrema, which I have this word at the end. The extrema, something you'll work with a lot. It helps you graph things. So relative and absolute minima and maxima, everything has A's, and that's the plural. So it's a minimum, and the plural of minimum is minima. And then we have maximum, but the plural of maximum is maxima. And then we have extrema, extremum, extreme, I guess. I'm not sure about that one, actually. That's funny. But when you have more than one, it's all the extrema. So if you think about relative, relative in this case could mean local. Some textbooks will use that word, local. So I kind of think of it as in like a smaller neighborhood. The word absolute, if you're looking for an absolute minimum or maximum, you're looking for the global. So of all things, like of that graph, absolute max would be the absolute highest point ever, and the absolute minimum would be the lowest point ever. For a relative max and min, those are just like, well, there was a maximum here, but then it started to decrease again. For a relative minimum, it's like, well, it was decreasing, it reached this relative minimum, but then it started increasing again. It does not have to be the highest or lowest of all points. And you can see the picture here. We have two relative maxima. We have two relative minima, just kind of self-explanatory. Relative and absolute maxima and minima. So again, if let me just grab my pencil tool. What I'm doing is I'm reading it from left to right. So it's starting from negative infinity and it's going up here, and I can already tell it's not the highest point, and that's probably why this dotted line is here. It's not the highest point because I can see the graph goes up higher than that. So that's going to be one of my, whoops, I want the text. That's going to be relative max. So relative max of 3 at x equals -1. Oops, I wrote -2. And then as I go, again, reading from left to right, I'm skiing down. So I can see this whole interval here is decreasing, right? It's decreasing. So let me go back. In the beginning, we were increasing. We hit our relative max. Now we're decreasing. And right here, where we go from decreasing to increasing, I know that's a relative min. And I know that because, again, it wasn't the lowest point. It's not the absolutely lowest point. Okay, so we can just add that into our list here. So we have a relative minimum of -3 at x equals 1. And then for this, we wouldn't have any absolute maximum or absolute minimum. And that we know because when we look at this graph, the way that it's shown to us, this arrow says it's going to go down to negative infinity. So there's no way it's infinite. So it's not going to bottom out or top out anywhere. Same thing here. This goes up forever onto infinity positively. And so there's no absolute highest number because there's always a number bigger than that in the infinite cosmos of math. Okay, let's go forward. Relative and absolute. So basically I could have just said, what are the extrema here? So again, reading from left to right, I see that it's increasing in the beginning. It's coming from negative infinity up. So it's increasing. And it does look like, oh, there's something funky going on here. but it doesn't change. It's still increasing, like increasing, 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 increasing. We just had like a change in the rate of how much it's increasing. So that means that for this one, there are none. So that could be a potential answer. So there are none. All right. I should have used the text tool. I used to be much better at this. All right. So there's no extrema in that one. And I think this is the last part of chapter 1.5. They want you to learn what even functions are and odd functions are. So a function is said to be even if it has symmetry with respect to the y-axis. Why didn't I use the text tool? Let me just grab that. And a function is said to be odd if it has symmetry with respect to the origin. And we previously knew the test for that. How do we test for symmetry? We did that in a chapter or so ago. So this is the same test. So I plopped it in here into this presentation anyways. And let's see. So then let's do some of these problems. Okay. Switch over. So we're determining if the function is even, odd, or neither. And again, feel free at any point to hit pause and try it yourself. So this is the function they gave us. Here's the test for even, there's the test for odd. So to find out if it's an even function, what we're going to do is g of negative x. We're wondering if this is a true. This is kind of the formal notation. If we have negative x, and that's what we're going to do in a minute, does it come back to the original? So remember, for symmetry, we take this, we rewrite it wherever we see an x, we put in negative x. So I'm going to put in negative x cubed minus 5 times negative x. And I'm going to change the g of x back to a y, just because that's how we looked at it for symmetry. And I think for some people that's just more comforting. So now I can simplify this part, right? The right-hand side, if we cube something that's negative, it's going to turn out to be negative. And then we have negative 5 times negative x. So that's going to be a positive 5x. And then remember again, for symmetry, what we're doing is, are these two things equal? This is our simplified version. This was our original. Well, we can see that the signs have changed on the right-hand parts of our equation, but not on the left. So we know that this is not even. It's really, really warm here today. It's New England, and we're in the day 3 of a heat wave. Okay, let's check for odd. For odd, what we're going to do is we're actually going to take what we just had, and we're going to see if it's the same as if we have a negative y. So let me rewrite this. Here's our original equation, and I'm going to change the g of x to y. So I'm just copying this. Y equals x cubed minus 5x. And to test for odd, we put in a negative y and a negative x. So there's a y. I'm going to make it a negative y, negative x cubed minus 5. So again, everywhere I saw an x, I changed it to negative x. Everywhere I saw a y, I put a negative y, because that's the test for an odd function. Now we just simplify. I'm going to keep the negative y the same. Same as before, negative x cubed turns out to be negative x cubed, and that turns to positive 5x. So we're comparing the original to my new one. And for me to be able to see it more clearly, I mean, this is an honors class, so you should be able to tell, but just since you're new at it, this is positive, this is negative. So I want to ground this, and I want to make this become a positive y. And the way to legally do that, the reason why I'm going to do that is so that I can compare it better. And how I do that is by multiplying everything by a negative 1. So negative y times negative 1 is y. Copy the equal sign. Negative 1 times a negative x cubed is x cubed. Negative 1 times a positive 5x. Okay, so all this work here below that line was all just plugging in that negative x and negative y. So now I want to compare it to the original. y, x cubed minus 5x. So yes, this is an odd function. It has symmetry to the origin. Okay. So same thing, new equation. Here's our parent function. Again, if it helps people, I will just get rid of the function notation and rewrite it. That's our parent function. To test for even, anywhere we have an x, we put in a negative x. So copy the y, negative x. All right, this can simplify. Any negative thing times itself becomes positive. And so if we compare that to our original, we can see that they do match. So yes, this is an even function. Okay, and just for the process to go through, even though we know that this is not going to work, I'm going to, again, here's the parent function. To test for whether it's an odd function or not, put in a negative y for y, put in a negative x for x. When we clean it up, negative y equals any negative thing times itself. And again, to be able to compare these better, I'm going to get this to be a positive y. And I do that by multiplying everything by a negative. And all that does is change all the signs. And so we're actually comparing this guy with this guy. And we can see that they are not the same. All right. All right, that should do it. If you have any questions, go back to the textbook, and I would go through that first and see if that has anything that is clarifying. There's definitely examples in the textbook. I don't go to the textbook and use the same examples as them. I want it to be a resource for you. So read through the textbook, look at the examples there, and there's definitely some assignments to do. So work on that. And if you have any questions, just send me a quick email.